Hello everyone and welcome to the DIANA webinar. My name is Maz and today I'm going to talk about general features and capabilities of DIANA based on our new release DIANA10. I quickly go through some of the features and capabilities, and at the end, if we have enough time, I give you a live demo on modeling a 3D box girder with pre-stressing load to give you some sort of insight about the modeling process in the new environment. So, the name of DIANA gets back from basically two technical words, displacement analyzer, these two words forming DIANA name. And it's a general finite element program which is dedicated to all types of civil, geotechnical, and oil and gas applications. So if you're working in a multidisciplinary company or in a kind of organization with different departments, which are part dealing with the infrastructure, another one dealing with the underground structure, so DIANA could provide the best platform for you to make one model associated to the structural part or to the geotechnical part, and different group can work in a one continuum and fully coupled model. We are quite active in different areas, including the technical sessions, providing technical sessions, training, online sessions. Most of our online sessions, almost all of them, are free of charge. We have dedicated training based on different topics. Please visit our website. And also, we do contribute to lots of known and international conferences by means of ourselves with the booth, and by our partners and clients who are using the program, and we submit a paper to present the up-to-date and optimized solution for the engineering challenges. This is a quick overview about some of our key clients from different fields, from the big construction companies, research organizations, governmental body, oil and gas industry, and also green energy fields also are quite active and using DIANA for instance, modeling the wind turbine, offshore or basically onshore projects. So, let me focus on different applications that you may consider DIANA as a solution for your project. Let's start with geotechnical and tunneling. Based on the complexity of urban area, any new construction requires consideration of three-dimensional effect and the impact of the existing structures on the new construction site. So therefore, the importance of modeling 3D becomes more and more pronounced. DIANA provides one platform for you that enables you to model 2D or 3D type of projects in this field. Ground freezing, nonlinear soil structure interaction. So beside of conventional type of nonlinear springs, in DIANA we do offer nonlinear constitutive models associated to the interface elements, and you can consider these type of elements and behavior to simulate the real nonlinear effect to the structure and the soil. Fully coupled groundwater flow is the effect of seeping and basically deformation and failure of structure. Deep excavation and temporary structures. Pile foundation based on our dedicated pile elements based on different type of characteristics that you may consider for the pile. And also earthquake, blast, and vibration analysis. Consideration of the drain or undrained behavior of the soil depending on the rate of loading, large deformation and large strains, and also consolidation and embankment, also another field of geotechnical and tunneling and indeed mining, for instance, slope stability to generalize and check the stability of the soil, which are on a daily basis in these groups can be used for the geotechnical tunneling and mining. On the other hand, DIANA also is very well known and has a very well reputation for reinforced concrete structures, and this is mainly because of the consideration and all the capabilities that covers all the process for the whole casting, curing, serviceability, and also failure and post-failure behavior of these structures. Therefore, you can consider DIANA to simulate all types of concrete box girders, composite structure, that means interaction of all types of steel and concrete dam structures because of mass amount of concrete, and also caisson, for instance, that type of foundation. Design check for reinforcement also based on the model code that we do offer to check the amount of reinforcement are complying the requirements from the model code, and the amount of space, the amount of crack that is occurring in the model also are in line with the limitation that model code offers. Simplified nonlinear analysis also is one of the strengths that we offer in DIANA for the practical engineers who do not want to enter into deep nonlinear setup of the model. So what does that mean? With the sequential linear approach based on the amount of damage that is occurring at each Gauss point, we have a reduction of stiffness for those elements at those Gauss points. So with this iterative procedure and increment of the load, we gradually lose the strength, and basically you can predict the failure of the structure with a very good prediction with respect to crack bandwidth and the failure mode. Temperature and stress development during the hardening of the concrete segment. So young hardening, as I mentioned, is one of the key factors that you may consider for the whole process. So when you deal with the young hardening, you're talking about gaining strength, maturity, aging, and also, as here is mentioned, the temperature and the basically strength dependency of the material property with respect to time and temperature can be considered. Cooling pipe can be modeled to control the developed temperature inside the model. And one of the key strengths is our embedded material models, which are dedicated to simulate different crack phenomena in the concrete. This crack initiation and propagation, we will go back to that in the next slides, enables you to basically identify the whole crack pattern, the crack strain, and also crack opening. And based on that, you can see the nonlinear failure and post-peak failure. That's the most important compared to other solutions that are available. Post-peak failure till completely rupture of the model. Effect of fire on the reinforced concrete slab also is another, or basically concrete structures also is another important factor that you may consider to develop or consider the development of the temperature gradient in the concrete structure and segment, and based on that gradient you can see and find out the effect of failure or the nonlinear structural effect. DIANA also is very well known for simulation of masonry and historical structures. Any masonry structures which are, or historical building which are subjected to the earthquake can be modeled based on DIANA, based on dedicated material model and different techniques that we have. These models can be simulated based on two levels, either meso or macro. So literally you can model everything as a continuum model, or you can model them based on the individual bricks and mortar in between. For dams and dikes, DIANA also has a very well reputation, and that's because of the coverage of all aspects of modeling the structure, the dam body, and interaction of that with the foundation, and also dynamic and fluid structure interaction and HFDD, hybrid frequency time domain analysis. So DIANA provides a unique solution for all types of dam, including arch dam, gravity dam, CFRD dam, and so on and so forth. For fire analysis, as I mentioned, this fire analysis could be fully coupled or staggered to simulate the effect of development of the temperature on the strength of the material and failure of the model. For earthquake engineering, we have a frequency response. Transient analysis could be time history linear or nonlinear. We have hybrid frequency time domain. This is the most famous feature that we have in DIANA for complex type of analysis, because you can perform two domains, one is frequency, another one in time, in a fully coupled approach. And basically for the models with the reservoir, you can consider the incompressibility of the fluid, and for the models, for instance, with the soil and superstructure, you may consider the part of parameters that are for the soil. You have them based on the frequency, and part of the material for the superstructure, which gonna be failed or cracked, for instance, in time. Fluid structure interaction enables you to exactly perform the hydrodynamic pressure on the structure, and liquefaction analysis is based on the liquefiable material models that we can assign it to the sand and soil material model. So we have that based on different constitutive models. Among the advanced applications in the oil and gas industry, DIANA also is very well known for simulation of the reservoir depletion, borehole stability, casing integrity, and basically for nuclear facilities also DIANA has a very well reputation because of full coverage of soil structure interaction, capability of nonlinear dynamic analysis, and also the three-phase analysis, the high temperature, soil structure interaction. All those things can be considered in DIANA. So, new version of DIANA has this look and feel. Similar to any other program, on the top we have a series of toolbars, and based on each of these icons you can set up your model, you can generate your model. On the left hand side here we have multifunctional window that basically keeps the record and history of your mesh sets, elements, material properties, loads, boundary conditions, and the combination of them. On the bottom left, we have a property window. In the property window, you can basically customize the parameters for or associated to the selected items from the multifunctional window. One of the outstanding features that we have incorporated in DIANA10 is our Python scripting. This Python scripting dialog box enables you to write your own Python scripts, or you can basically rerun whatever you have done in the modeling process, which are scripted automatically in a Python language. You can modify that and rerun that in the model. The message dialog box literally gives, or basically is a window for communicating with you. In this dialog box you can see all the messages, warnings, errors, and some output information during the analysis procedure. On the right hand side, on the top part, you can see the analysis setup window based on the different types of analysis. It's very intuitive. You can set up the analysis and perform the analysis based on the sequence of them. And under that or beneath, there is a post-processing dialog box that enables you to visualize your results based on the contour plots, vector plots, clipping plane, slicing plane, and diagrams, and indeed tabular output. So what are the outstanding features for the DIANA interactive environment? It's very intuitive to use, very user-friendly. We have implemented the Parasolid modeling tools in the new DIANA, and that's very powerful and make it really outstanding and pioneering in the modeling CAE programs. Also, we do have implemented the latest generation of mesh engine in the program that enables you to generate hybrid mesh, basically mesh sets for you based on the hexa dominant modelers. And also we have enhanced the process of modeling reinforcement, embedded reinforcement or tendons or bars, and also creation of interfaces. For loads and boundary conditions, we are talking about capability of various types of loads and boundary conditions can be assigned based on different coordinate system, including manual one. A new definition and procedure has been introduced regarding the boundary elements for thermal or groundwater flow analysis. You can easily define functions for the model. These functions can assign to the loads. That means load is varying with the geometry, and also these functions can be introduced in space. So basically, based on the X, Y, Z, you can define this variation and assign them either at the material level or to the load or to the geometry. For the post-processing, we cover a comprehensive set of output, including the contour plots, diagrams, tabular output, slicing, so I can show you in a live demo. In order to define the material property, we do have two levels. The first one is the material class and material type. In the material class, you may say, I'm dealing with the concrete, I'm dealing with the masonry, I'm dealing with the steel. And in the material type, over there, you can select and assign the correct constitutive model associated to that material class. Furthermore, and to optimize your input parameters, we have aspect dialog box, and in this aspect basically dialog box you can activate the additional inputs which are required for that particular analysis, and you can basically, based on the radio button, you can check them on and off and accordingly you can see some inputs which are active or inactive. Load combination is another interesting or useful feature from the design aspect as well, and also from the nonlinear aspect. So you need to set this load combination before performing the analysis. Functions we discuss about that. Property windows enables you to basically manually control the parameters and change them based on the selection of the multifunctional window. And indeed, for the analysis window, there is a very interactive approach, especially for the phase analysis, to basically enables you to deal with the complex or various number of construction stages that are required for your analysis. So what I need to highlight at this moment is our workflow for DIANA10. So what does that mean? That means from DIANA10 onward, our whole modeling process is kind of mesh independent. What does that mean? That means we set up the geometry, we define load boundary conditions and imprint the position of them on the geometry. And after that, we assign the properties to the geometry. For instance, if you have a concrete block, you say, okay, this block, this solid block has a concrete property. Then you literally, before performing the analysis, you create a mesh for that. It's automatic generates the mesh. And then you perform the analysis and check the results. So before running the analysis, you don't need to do anything with respect to the meshing. Everything is defined at the geometry level. So this makes you more flexible and basically free in terms of changing the model or adapting it because you are mesh independent. So let me talk about the whole process that we discussed. Starting from the geometry modeling, you can import the CAD model files, and also you can import other file formats according to the Parasolid step IGS files. You can easily import them. You can use our primitive modeling features to generate 3D models, 2D models, and 1D models, either solid or sheet or lines and points. You may consider Boolean operation to interact and intersect different segments with respect to each other. You can transform, scale them, rotate them after all these segments generated. We have a smart selection filter. Based on the selection filter, either it's face or solid or line or point. If you open a window over your model, it automatically selects the specific icon that you already highlighted from your selection window. We do offer automatic clash detection. This is very important if you're dealing with different segments which are interacting and intersecting with each other. Therefore, using this automatic clash detection enables you to ensure you have final proper nodal connectivity between different model segments that you have and different geometry segments that you have in the model. You may convert your solid to the closed shell or closed shell to solid based on the associated functions. And as I mentioned, imprint function is one of the most important because if you define a load or boundary conditions, you need to imprint the position of them on your geometry before defining the load. So you need to, if you have, for instance, this type of distributed line load and these 2 point loads, you need to know where are they on your geometry, imprint this line and these 2 points on your surface, and then assign the edge pressure and the point loads on these geometry objects and imprints. You may use rotate and move faces and shapes and make it quite flexible by variation of each side and each face. You may extract faces from the solid. You can use the extrude to make extension of the solid. And you can align different geometry objects with respect to different positions, coincident, coplanar, parallel, concentric. So you can basically consider all those alignment with different options that are available. Regarding the function I mentioned, this function can be assigned one of the things at geometry. So if you have a shell element and you want to model, for instance, a bridge like that, you may define a shell, but you change the variation of the thickness using a function as you go through the length or span of this bridge. So you can mimic this type of behavior using a function. Our mesh generator covers basically hybrid meshes, so these are the different types of mesh sets, unstructured, structured, and hexadominant mesh sets. And you can see the quality of them. They're absolutely optimized with respect to the geometry, and you can use them based on various complexity that you may have at the geometry level. For online documentation, that's also another important field that we always keep that up to date based on the background theory, based on the tutorials, based on how we have implemented some of the concepts in the DIANA. What are the examples? So you may refer to this manual and always check before proceeding with the modeling. So regarding analysis type, DIANA offers various types of analysis associated to your models. I briefly go through them. Linear static analysis is one of the most common one, and also you can combine that with the moving load analysis for the bridge engineers, fatigue failure analysis, and also 2D and 3D linear elastic fracture mechanics. So these are the additional features that you may consider under the linear elastic analysis. For nonlinear analysis, we have different definitions. This nonlinearity can be defined at the material level or at the geometrical level, or this nonlinearity can be defined with time. So you may also consider the nonlinear approach on implementation for contact analysis. So by variation of the load, the algorithm that finds a new contact surface is a nonlinear, therefore you can obtain the contact, you can perform contact analysis, which is nonlinear analysis. For dynamic analysis, we have frequency response analysis, a series of linear approach. We have basically time history analysis based on the linear or nonlinear one, and HFDD analysis, as I mentioned, basically the combination of two domains based on the frequency and time, and indeed fluid structure interaction to accurately predict or mimic the hydrodynamic pressure acting on the structure. For stability analysis, either general Eulerian stability or perturbation analysis and continuation analysis are available to consider, for instance, buckling or post-buckling of your thin shell models. We have a concept of potential flow analysis in DIANA, and this potential flow could be assigned to the basically heat or could be assigned to the groundwater flow. If you're dealing with the heat flow, then we are talking about basically conduction, convection, and radiation. And at the material level, we have a time, temperature dependency, and also contamination transport, also another feature that can be considered. This contamination transfer is a 2D, and you can trace and track the particles in your medium. We have also Reynolds flow lubrication analysis. This is a mechanical concept, but literally you can mimic the heat generated from the rubbing and movement of your bearing and the support. After performing the potential flow analysis, you can combine and find the impact and effect of that on the superstructure. So that means if you have some sort of groundwater flow analysis, the development of the pore pressure, you want to see how this affects the failure of the superstructure. So we have either staggered analysis, that means first you perform potential flow and then nonlinear structure, or you can have a coupled approach. Then in that case, program solves PU or TU for you. For phase analysis, we consider the full process for the construction or erection of the structure or decommissioning and basic demolishing of the structure. Moreover, you can combine this concept of phase analysis with potential flow. For instance, you want to see the variation of the effect of the nonlinear effect on the structure in time. So after 10 years, 20 years, changing the season, how the model is behaving, how the crest, for instance, in this dam is changing. Beside of those conventional types of analysis, we do have additional features like random field analysis. I will talk about that. This is very useful model to introduce heterogeneity in the model. Stiffness adaptation, as I mentioned, to predict the failure and post-failure for your model without entering into the nonlinear analysis, parameter estimation, probabilistic analysis, and indeed liquefaction analysis. We do have more than 250 elements covering all dimensions, 0, 1D, 2D, 3D, and a specific type of elements, low order, high order. And these elements can be combined with different types of analysis and also with respect to each other. Moreover, we at DIANA is one of the first developers about the concept of embedded elements, and we take benefit of this concept for simulation of bars, tendons, embedded piles, and also we do have matrix reinforcement for mass volume that you can basically smear the reinforcement in your volume. For the pile element, not only we do have embedded pile element, we do have embedded pile tip to simulate if you have some sort of pile design with the pile tip failure, you can easily consider that effect in your model. One of the feedbacks that we get from the analyst and the designer is the definition, because the analysts usually, when they do finite element analysis, they get stress and strain, while the designer usually looking for bending and shear basic sectional forces. So to introduce the new language or common language between different interests, we came with the concept of composed line and composed surface. So if you have a plane stress beam here and you do some sort of shear analysis, shear bending analysis, you may come up with some sort of shear and basically stress and strain in the model. Using the composed line enables you at the same time to extract the shear force, the developed shear force, and the corresponding bendings in this beam. So therefore, the designer will take and look at these parts, and also the analysts look at the contour plots associated to the stress and strains. Similarly, for the composed surface, enables you to obtain or embed this composed surface in your solid and obtain distributed moment and forces which are needed for the design. For material models, we do have more than 150 material models: linear, nonlinear, modified elasticity, hyperelasticity, isotropic and orthotropic plasticity like hill plasticity. We have viscoelasticity and viscoplasticity. So if you are dealing with the creep, you may consider for the concrete viscoelasticity. If you are dealing with the landsliding or avalanche, for instance, you may consider viscoplasticity. We have various crack models and approach, discrete or smeared one. We have concept of creep and shrinkage, time, temperature, and maturity dependent, and also liquefaction analysis. If you are not satisfied with all these constitutive models, we have a user supplied subroutine that basically you can write your own constitutive model and perform the analysis and use the existing features and capabilities that are available in DIANA. So for crack model, we do have different approaches. These crack models could be based on the discrete crack model, which that means you can see the crack beforehand on the structure, and you want to see how these cracks are opening, closing, or sliding by variation of the load. In that case, you may come with the concept of interface and dilatance interface or discrete interface to see and mimic this effect. However, in most of the cases, we are dealing with the continuum model, and in the continuum model, we don't know based on the increment of the load or variation of the loads how these cracks are initiating, how they are propagating, and how these could end to the final failure of the structure. For that concept, we have a smeared crack model with different formulation, multiple fixed or total strain. And also we are dealing with the fiber material models. So different types of fiber material models can be introduced into the program, either basically synthetic or steel. And these fiber material models can be combined based on the recommendation of the model code SEPFIB. So you can basically obtain three type of failure point and define based on stress total strain or stress crack mouth opening, and proceed with the rest of the analysis. Random field material model enables you to simulate or introduce heterogeneity in the model. So based on the basic compressive strength of your concrete, it calculates the rest of the parameters, and based on the log norm or any other approach that we have, it generates the basically random field to your model. And this way you can localize the failure and crack in the model because of these variation of, for instance, the strength in the model. One of the key factors for instance, total strain model is you can easily drive all the materials from the model code. So you can say my grade of concrete is C40, and program automatically drives all the required material, including tensile strength, compressive strength, fracture energy, and others. While in DIANA we do offer full capability to modify all the features and capabilities in terms of tension softening, compression part, and tension, basically moving from biaxial from tension to compression, all those things, and shear retention to adapt and adjust the behavior as close as possible to the reality. So all those predefined parameters can be overruled by user. For creep and shrinkage, we have different concepts. This could be metal creep, transient creep, or viscoelastic creep. And for shrinkage, this shrinkage can be defined based on the shrinkage strain and time as a user-defined function or table, or based on the model code. Based on available code that we have, you may refer to that, and program automatically interpolates the corresponding contribution of the shrinkage strain to your model. When you have different segments and parts which are connecting to each other, we are talking about spring dashpot elements, and these spring dashpot elements can inherit different characteristics like linear elastic spring, nonlinear elastic spring, considering loading, unloading, and reloading, plastic springs, subgrade reactions, and also various nonlinear dampers that you can combine them with, for instance, springs. But as I mentioned, beside of all those characteristics, the key factor is definition of interface in DIANA. So you can interact different segments based on the dominant characteristics with interface elements. This behavior could be linear or nonlinear. Cracking behavior, as I mentioned, for discrete or dilatancy. This interface could carry the characteristics of bond slip, Coulomb friction, and CSC. This CSC is one of the famous material models that we have and developed based on the initial work of Professor Lorenzo for modeling mortar material model. And this one can be used also now for 3D, and literally you can model the discrete approach of your masonry structure by using this type of interface representing your basically mortars and joints. Excuse me. For reinforcement and bars and cables or tendons, we have different characteristics. This could be linear elasticity, could be plasticity, could be hysteretic models to capture these energy-dependent material models. And for tendons, you may consider the grouting and no grouting effect. And also for the soil material model, we have different initialization procedure based on the K-node or based on the initial field. We have poor pressure modeling considering drain or undrained behavior depending on the rate of loading, and also variation of the phreatic water level as automatic or user-defined level. This is a quick overview on the soil, rock, sand material models, and literally you can have an overview on these models. And if you are not satisfied with all the existing material models that are associated to the soil, concrete, steel, and basically bars and interfaces, you may write your own constitutive model and compile it and run it in conjunction with the rest of features and capabilities that we have in DIANA. For load and boundary conditions, DIANA offers a huge range of options. So these loads can be worked on the body, nodes, pressure, pre-stress, post-tension, and also varying with function. Similarly, you can assign the same thing to the boundaries. These boundaries could be static boundaries, that's like constraint, or basically hydraulic boundary conditions, which are basically variation of the pool pressure or the head that you may consider and assign them to those. Your outputs are compatible with tables, and also tables are compatible with Excel. Also, some of the inputs for the function, for some input parameters, all of them are compatible with Excel, so you can always exchange the information between Excel and DIANA. From the solution procedure, DIANA is, I think, the only program that offers the multiprocessor at no additional cost. So these multiprocessor, you can take advantage of them for linear equation solver. We call it Paradiso, parallel solver, and also for eigenvalue solver. This parallel solver also available for that type of big models. And for nonlinear equation solver, we have a nonlinear solver to handle nonlinear analysis. When we are dealing with the nonlinear system, we are talking about different iterative procedures. These iterative procedures are basically based on linear or constant stiffness, regular or modified Newton-Raphson, secant method. And also the approach for the solution could be load or displacement control, arc length control, line search algorithm, and also adaptive load and time increment. For Python scripting, this is a generic language, so you can always have access to that from any online publications or reference books. But in DIANA, you can write your own Python script to generate the model, to go through different analysis, perform sensitivity analysis, and always try to take benefit of these powerful feature and tools that we offer in DIANA. Finally, in terms of the platform, we do offer DIANA for basically Windows and also on the server, so you can see, and Linux as well. So you can find all the available platforms in this slide. And the last thing that I would like to raise is our quality assurance. So every night we are going over more than 10,000 regression tests to make sure that the new developments that on a daily basis our developers are taking into action are not affecting the existing verified and calibrated performance of the program. Among them, there are 5,000 are available in the D-test in your installation. So based on the variation and the combination of the elements, analysis, loads, material types, you can combine them and see how you can set up the model and analyze them. But these 10,000 is one of the automated regression tests, and if there is anything, it automatically reports to the developers, and based on the narrowed down report at which day, which line, which part is modified and is affecting other part, the developers is basically is assigned to go and fix that modification. So every day we have these regression tests. So let me go through one live demo. What I'm gonna do, I'm gonna make one box girder. Let's do that together. It's a simple example, but I hope you get some sort of feeling and insight about the modeling process. So this is the look and feel of DIANA. I make a new project. So in this dialog box, you can set up the name of the project, where do you want to store the file, what type of analysis you want to do, because if you're doing structural, heat flow, groundwater, and without basically selecting them, the corresponding fields and inputs and element types are not active. So always use the optimized functions and features which are required for your analysis. So I'm going to do one linear static analysis for box girder. The type of dimension is 3D, and also the corresponding modeling box is 100 by 100. And I'm dealing with the linear order for the elements and hexa model. I changed the name of my project as a box girder and click OK. So as I'm making my model here, you can see there is a scripting process for the Python. So I already mentioned my name of the project, the dimension of the modeling, the type of analysis is structural, and also the dimension of the model 3D and corresponding and so on and so forth. If I go to the reference for the model, here you can always check your units for the length, for the mass, for the force, for the time, temperature, and angle, and also the dominant direction. So if here, for instance, you say, what are my X, Y, Z, you can always define them here. And in terms of the principal definition, we have a predefined acceleration gravity and also always direction in Z. So in this particular case, just to show, I'm changing it to Y. So that means my gravity is now changing. So my model is in basically X, Y, Z. So the gravity works in Y direction, just for sake of showing. So I start to make my model. You can create a sheet, and here either you can input XYZ coordinates, or like me, based on the corresponding XYZ, you can copy them from the Excel and go back here and place. If I change my view to the top, you can see my outer position of my box as a sheet. Now I'm going to make the inner part, once again based on the reference coordinates that I have. So to speed up, I easily copy and paste it directly from here. So you can see the inner part also is generated. So what we're going to do next is we're going to subtract. We're going to subtract the inner part from the outer part. I go to the subtract icon. This one is my master. This inner part is my tool, and I'm going to subtract. Click OK. So this is my subtracted, or say it, cross section of my box girder. The next step is extrusion, because I'm going to model a 3D for you. So I click on extrude. I select my box, and you can see if I drag the dimension that I'm dealing with, you can easily extrude the model in any direction and any dimension that you want. So you can drag the corresponding basically axis and come with the three-dimensional model. In this case, I'm gonna drag that 10 meter in the direction of my Z if my Y is the gravity. Next thing is defining rebars. I define some bars on the top of the web. So I define line, the starting point are 0 and the end point is minus 4.5, 2.85 and 10 as full length of my model. So here you can see if I go back to the geometry and hide my sheet, or say the solid model, you can see the first line that I generated. The next thing that I'm gonna do copying this, multi-array copy. So what I'm gonna do, I'm gonna select this line, relative displacement, I'm gonna copy that in the X direction with the distance of 1.5 meter. And 6 times. So you can see it automatically generates 6 times your tendons. So if I show my box, you can see the position of them here in the model. So the next thing is defining the position of support. To create a support, I make one single plate, I copy them, multi-arrow position the 4 bearings, and then imprint these slabs or these faces to the bottom of this box girder. So let's do it together. I go to the sheet, I copy the support sheet coordinates, and here, so you can see it generates this one. What I'm gonna do, I'm gonna copy this sheet or the position of the bearing from here to here, and then copy these 2 all the way to position here. So the first one that I'm gonna do is the movement of that with respect to say it multi-array copy. I'm gonna select this, and in the basically X direction I go minus 3.6 backwards. So now I have 2 sheets positioning the bearings. I'm gonna copy them and move them in the direction of Z, 8.5. Okay, nice. So we have the position of these bearings here. But if you see, if I hide these bearings, there is no imprint of them on this concrete. So as I mentioned in the presentation, I'm going to imprint the position of them on the concrete. So I go for imprint, select the face, the bottom part is my basically target face, and the tool surfaces will be these 4 surfaces associated to the bearings. But here you should be careful because we changed the orientation. Now we have to do that in minus basically 1. So basically in the direction of y direction. So 0, 1, 0. If I click OK, so now you can see those sheets are disappeared, and whatever you see here is imprint of those bearings on the concrete body. So we are almost there. What we need to do, we need to assign the property to the geometry. I go to the assignment of the property, I select the box, I tell what type of element is that, is structural solid, and in terms of material property I say the name is concrete, and the class is concrete masonry, linear type, and I don't deal with any aspects at this moment. I click OK. And what I need in terms of basically constitutive models is one Young modulus, 2.4 for instance, E10. Then I have 0.167 and mass density because we're going to consider the effect of self-weight. Click OK. So the concrete material property has been assigned to the box. I hide the box, and now I'm going to define reinforcement assignment or embedded reinforcement to my lines. So the material is different here. Bars, reinforcement, linear elasticity. I click OK. So what is important here for me is only the Young modulus. So I consider 1.96. E11 and click OK. For bars, what else we need is a cross-section area. So I need to add this cross-section area associated to those bars as long as they are carrying the same attribute to all of them. So I define that cross-section of area and click OK. OK. So now you can see automatically all those lines at the geometry moved under the reinforcement categories. So we do have this material property assignment. Everything is in place. Now the next step is defining our support. So for defining the support, you need to go to the corresponding part. I remove the previous selection. I call it BC as a boundary condition, assign it to the mesh and geometry. The type of selection is face, so I select the position of them here based on X, Y, Z with clamp just for sake of illustration. So you can see the position of them. I go and define the body force as self-weight. So by default, we do have the ground acceleration 9.81 based on the unit that we have. What was important was the direction of the effective direction. So I manually changed that to Y, but the default is Z. And here also I call it self-weight, and that's it. You click OK, program considers self-weight, and already you define mass density to the model, and program basically considers that as a part of the contribution. Beside of that, I have a pressure load. Or say it like a traffic load on the top. As a face, I select the top face, uniform distributed. Say the value of that could be 4E9, but the direction is in the Y direction. Maybe I change that to 2.0E4. Click OK, so you can see the impact and effect of the traffic load on the model. Then we have pre-stress load. For sake of visualization, I hide that. pre-stress. We change that to the reinforcement bar pre-stress. I select all of them, and the amount of pre-stress is 4E9. Okay, so everything is ready. I'm gonna seed my model. With the element size 0.15, click OK, and now we are ready to define a mesh. I click on Generate Mesh. So I had one self-weight, I had one traffic load or pressure on top, and I had a pre-stress for the tendons. So I have 3 separate load cases, which I'm going to make one new, literally basically load combination, and based on that we're gonna perform the analysis. So this is the quality of the hexadominant measure. So I go to here under the load, I add a new load combination and consider the effect of everything together with the factor of 1. So you can customize the factors and impact of them separately. I make a new analysis, linear analysis, perform the analysis for that. It takes short period. So under the self-weight, because we have different output, self-weight, pressure, pre-stress, and combination of them. So see, for instance, what's our deformation. We can see that when the model is subject to the load, when it's subjected to the pre-stressing, and when we have a combination of that. And also, when you're in this field, you can use, for instance, clipping plane. And in this clipping plane, literally what you can do, you can, in a real time, cut your model at any angle, any rotation, and see what is the variation of the results in the model. So this was a quick overview about the features and capabilities that are available in new DIANA, how easy you can set up the model, any 3D model, how you can set up the analysis, how you can customize that, and see the results. So I hope you could find it informative. I'm available. If you have any questions, I would be more than happy to answer them right now.